Hello, everyone. Thank you for attending today's webinar titled Anodizing Basics for Aluminum and Aluminum Alloys, brought to you by Products Finishing and presented by the Aluminum Anodizers Council. I'm your moderator, Scott Francis, editor of Products Finishing. Today's presentation will last approximately 45 minutes and offers an overview of anodic oxidation and comprised of three parts: anodizing circuit, oxide growth, and anodizing strategies. A question and answer session will follow the presentation. If you have a question, you can type it at any time during the webinar in the Q&A section of the chat. The webinar is being recorded and when complete will be made available to you via email from Products Finishing. Today's speaker is Dr. Judy Runge, whose career as a metallurgical engineer and surface finishing expert spans almost 40 years in industrial, government, and academic professional settings. Today, Judy is the subject matter expert for surface finishing for Apple, and her analytical experience and expertise encompass a variety of manufacturing processes for all materials and focuses on science and engineering of many aspects of metal finishing. Kicking things off, we'll hear from Jeff Henderson, president of the Aluminum Anodizers Council. Jeff joined the AAC in 2016 and since then manages the overall activities at AAC, and during his tenure has focused on the growth and well-being of the anodizing industry. To that end, the AAC has taken a three-pronged approach to its mission: promote and grow the industry, become better anodizers through education and networking, and advocate for the industry in areas ranging from worker safety to counterproductive regulations to free and fair trade. He'll lead our discussion with a brief overview of how the AAC is accomplishing these objectives. Jeff, I'll hand it over to you.
All right, thank you, Scott. So let me assure the audience that we will get to Dr. Runge in just a few moments, but first I wanted to talk a little bit about AAC and what we have to offer. In order to give you a full screen here, I'm going to turn off my video. The Aluminum Anodizers Council has three areas of strategic focus: advocacy and government affairs, member education, and industry promotion. In short, we aim to protect our industry, become better anodizers, and grow the industry. In advocacy, we look at environmental and legislative advocacy and continually on the alert for issues involving unnecessary or unwarranted or counterproductive environmental policies. Also, we support free and fair trade and have worked with sister organizations to this end. And we also believe in worker safety, and we advocate for that as well. In education, which is a cornerstone of the AAC, we offer 4 classes: Anodizing Essentials, which you'll hear a truncated version of one of the presentations from that class today by Dr. Runge. Also, Quality and Troubleshooting, Advanced Anodizing, both 1 and 2, and now in development to be released next year, Anodizing Process Quality class. In addition to these classes, we also offer education at all of our conferences and through webinars. In industry promotion, we offer industry-focused webinars, whether it's architectural, medical, whatever the application may be, to educate them about the benefits of choosing anodizing as their metal finish. We also have featured podcasts with interesting guests. Our podcasts were recently developed and are now released. So wherever you get your podcasts, look for Ano Talk, all things anodizing. And for years now, we've sponsored and supported a webinar for architects through the AEC Daily platform, which promotes continuing education units for architects. These combined efforts reach hundreds of influencers of metal finishing every year. I wanted to point out to the audience about our annual fall conference. Non-members are invited, but members get a discount to conference. Our conferences offer educational events, networking opportunities, and COVID allowing facility tours, and a lot of fun. There'll be an expo hall as well. This year, we are co-locating with the Aluminum Extruders Council. So this will be a very big event. We expect hundreds of people in Nashville this September. That'll be at the Sheridan Music City in Nashville. And we had a co-located event with the extruders back in 2017 and set a record on both sides for attendance. So we really expect a big event. So if you want to get to know more about the AAC, this would be the time to do that. During conference, we will have 4 focus tracks that'll include technical, colors, seals, innovation, and new technology. We'll also have our international student poster competition, where students from around the world put together a poster advertising the work they're doing in anodizing. These young students bring forward a tremendous insight into the development of the next generation of anodizing products and processes. And what most members really appreciate are the number of networking opportunities they'll have. And COVID allowing, we will have a plant tour. For members only, we have certain offerings, webinars that address how to become a better anodizer, environmental updates from our representative in Washington, D.C., technical bulletins and updated bulletins, the AEC Buyer's Guide, which reaches all of the industry promotion lists of all the folks who have participated in our industry promotion efforts. They'll receive a free copy of the AAC Buyer's Guide, in which members can advertise themselves and list themselves to be the vendor of choice for the next project. Members also receive significant discounts at conference, on the education classes, and they'll also receive our quarterly newsletter, Anodizing Newsline. The type of memberships that we have are for firm or anodizers themselves, also suppliers, and also associate members. And these are folks who purchase anodizing for the products that they manufacture. We also have a professional category. There are different levels to each of these memberships depending on certain criteria. So to get more price and availability information, either email us at mail@anodizing.org or visit our website, anodizing.org. Join the AAC because we are the only trade association where we are focused solely on the needs of the worldwide anodizing community. And again, visit www.anodizing.org to learn more about it. Thank you for your attention, and I'll turn it over to Dr. Judy.
Okay. Well, thanks, Jeff, and thanks, Scott. It's a great, beautiful morning here in California, and I'm here to talk to you about anodizing basics for aluminum surfaces. Our class goals are threefold. And the first is to develop a virtual picture of the anodizing circuit in order to understand the nature and mechanism for anodic oxidation, specifically for oxide development and growth. The second is to make the connection between substrate microstructure and the structure of the AAO. And thirdly, to make the connection between the anodizing circuit and the quality of the oxide structure. In short, by understanding these 3 items, we can connect the circuit to the mechanism of oxide growth and develop anodizing process strategies that target and optimize the characteristics of the oxide for a variety of design applications. In short, I'm hoping that your biggest takeaway today is how to make anodizing an engineering process. So anodizing has been around since the late 1800s. Today, we see it used in a variety of industries. We see it in the medical industry, as Jeff pointed out. In the medical industry, the oxide is primarily used for corrosion resistance when instruments are sterilized, but it is also used for its ability to be decorated and colored. That way, it can be used as an identifier for sizing for critical surgical tools that require a certain fit. Anodizing in architecture provides a living skin to the skyline. It is a beautiful, low-cost, durable finish that we see all over the world. The aerospace and aircraft industry, the industry with that aluminum itself grew with, utilizes and has utilized the anodic oxide finish for decades. This is for it in a variety of applications, for its ability to provide corrosion protection at thicknesses that don't impact fatigue resistance, to provide a surface for paint, for adhesion of other labels and identifying markers, for corrosion resistance, for decoration, for wear resistance, and heat absorption and reflection. In the automotive industry, it's used as decorative finish for trim inside and outside of vehicles, but it's also utilized under the hood for its excellent wear protection and impact resistance. The last example is probably the one closest to my heart, and that's utilizing it for the beauty that you get that showcases the appearance and feel of your consumer electronics, for your phones, for your computers, and other digital equipment. So now we've seen macro applications. What does the oxide look like? And here are two images that show you a top-down and also an end-on snapshot of the oxide and its consistency in size, shape, and organization. It is a self-assembled, highly ordered nanoscale network of individual electrochemical cells. So today we're going to talk about how that network order is achieved. How can the network grow? Because after all, this is an oxide. How can this grow after the substrate surface is covered? And how do the structural characteristics of the oxide develop and function? So let's jump into our class goals and get right into developing the picture of the anodizing circuit. If we look at anodizing as an overview, and this eliminates all the rinses, which are possibly the most important part of the anodizing process in general, we can compartmentalize the process into three basic sections: pre-treatment, anodizing, and post-treatment. Every step is electrochemical, but only the actual process of anodic oxidation utilizes an external power source, with the exception of electropolishing. Pre-treatment and post-treatment, therefore, because they don't use an external power source, are equilibrium processes. This means that the reaction at the surface is limited by the local reactants. When those reactants are used up, the reaction stops. Therefore, as engineers, we can time those processes to reflect the effects we intend. And typically with pretreatment, it's to maximize the amount of available free aluminum for anodizing. And for post-treatment, it's to enrich color or fortify the seal. Anodizing is a non-equilibrium process. The use of the power supply drives the reaction beyond equilibrium. Theoretically, there are no limits to what we can do during anodizing, because we can push with the applied current an infinite amount of aluminum ions to the surface for anodizing. This snapshot is of an operating anodizing bath. And even though I've superimposed several images and diagrams over it, I hope you can see that with the connection to the power supply in the lower left-hand corner, we've established an electrical circuit. The anode is positively charged and is connected to that flight bar, which is inserted in the saddle at the bottom left-hand corner. So take your view into the photo and see that circle superimposed over the circuit. The anodes are well within the electrolyte, and the electrolyte is vigorously agitated around the anodes. That electrolyte is the next biggest wire in the circuit that connects those anodes to the cathode, which are grounded but likewise immersed in the electrolyte. To operate this circuit, we need that power source. We need that electrolyte, which is typically a strong acid, and sulfuric acid industrially is possibly the most common electrolyte utilized. We need our parts and we need our cathodes. And as an aside, I just want to say cathodes are probably the most overlooked part of the circuit, but you want your cathodes to be as conductive as possible to maximize the efficiency of the anodizing circuit. Because that anodizing circuit drives the oxidation reaction, and that circuit obeys Ohm's law. So this slide may be the scariest slide for some of you for this presentation, but I promise you, everything comes together. We can model oxide growth because it follows a circuit path that obeys Ohm's law. This expanded version of Ohm's law, the Tafel equation, was specifically developed to reflect corrosion reactions. In anodizing, we are consuming aluminum in order to grow oxide. It is basically controlled corrosion. So what we see here is V equals IR, and this is written in blue below the more complex equation, which reflects N as the polarization measured in volts, the resistance of the anode times the combined currents of the applied current density and its change to exchange current density when we deviate or transition from the aluminum to the aluminum oxide, plus the resistance of the circuit that takes into consideration all of our process options that we control, times a more complex current density that includes the applied current density, but also that part of the current density that can be changed by the resistance of the circuit. So this is an important concept necessary to have in mind, even if you're just using the virtual picture of the anodizing circuit. There are three types of current density that drive this reaction: the applied current density that we set ourselves, the exchange current density that reflects the change in how that current is carried from teeny tiny electrons to bulkier, more clumsy ions that include aluminum ions, but only those aluminum ions grow and develop into the anodic oxide. However, we never or rarely anodize aluminum pure. We always anodize aluminum alloys. So we have to consider what changes are those alloying elements going to bring to the circuit when they don't participate or grow oxide. What they bring is resistance. That is measured in, is flowing in ions and is given by the quantity of the exchange current density. It is affected by the substrate microstructure because that is where our alloying elements are coming from, whether as a particle, a phase, a grain boundary, or a defect caused by deformation. Lastly, that limiting current density is a little bit elusive because what it represents is the flow of hydrogen to the cathodes. But those hydrogen ions have to transport themselves, driven by the applied current density, of course, through the oxide and then through the electrolyte. Think of all the things that can interfere with that and how that resistance can cause a change in the circuit. This should help us all be able to envision how that circuit operates. So what happens there? Remember the circle in the middle of the anodizing tank 2 slides ago? Well, this is that same circle, and we're going to focus our attention at that transition area around the anode. The applied current density that we set is what is utilized to transform into a polarized or voltage response. This is what sets the oxide column centers across the anode. This is done because polarization is a means by which within the electric field, the internal bulk of the alloy shifts to maintain charge neutrality as we are polarizing the surface as an anode. In other words, it has a net positive charge. These positive charges separate and concentrate at distances proportional to the circuit voltage. When we apply the current, as I mentioned previously, that applied current is carried by electrons in the aluminum. And then when we jump across the metal oxide interface, the exchange current density and that transition alone causes resistance, but every bit of the microstructure contributes some resistance and changes the applied current density to the exchange current density where it is carried by ions. In this moment, the oxide is nucleating and developing from these polarized centers. And that current is carried through the oxide and the electrolyte to the cathodes. This is where the current is primarily carried by hydrogen ions. And yet, all sorts of other extraneous interference can occur, integrating I sub L with the exchange current density. Nevertheless, if the circuit is unhindered, it will flow to completion. The ordered network will develop into that beautiful columnar structure that we recognize as AAO. I add this last comment because be not distracted by calling AAO a coating or a deposit. It is a growth. It is an integral part of the aluminum surface. So when we go finer and take an even deeper dive and look at each part of that equation, of that model, and we look at what the surface looks like as polarized, this schematic shows you the discrete oxide nuclei spaced according to the surface polarization. This should give you the insight immediately how that voltage response is going to govern the distance between the base of each column in the oxide structure. The number of nuclei depend upon the degree of polarization that corresponds to the voltage, and the charge is measured from center to center. So we flip the switch, we turn that current on, and guess what, guys? We have in equilibrium situations, we have a double layer. But when we push current through this arbitrarily set to our specifications, we make that double layer oscillate according to the spacing set by that polarization. This is the beautiful science of anodizing. It's not magic. It's not a miracle. It's truly science. As we pump those electrons through the anode and they hop across into the aqueous electrolyte, bam, we cleave that water and we have our hydrogen ions and we have hydroxide ions. Hydrogen ions are positively charged. They're going to flow to the cathodes, but those hydroxides, they're going to be pulled back toward the surface of the anode, and they are going to be concentrated at each polarized center. At the polarized center is where we have pumped all of our aluminum ions. This is where we start making anodic oxide. And the non-equilibrium beauty of this is because we have concentrated our hydroxide ions in the saddles of the polarization wave or the current density wave, and we have them concentrated against our concentrated centers of aluminum ions, we make stable oxide. We locally raise the pH by the concentration of those hydroxide ions in an environment that if this was an equilibrium process, we could not form a stable oxide. It would dissolve. So here in this schematic, get in your mind that this is where it begins. And those centers coarsen and develop and grow. But what about that exchange current density? Well, that red dot is going to represent something that makes this anode a little bit more complex. It changes the chemical potential at the surface. It changes, therefore, the resistance near the surface. So I sub A can no longer be purely what we set. It varies or changes based upon the quality of the substrate we present to the electrolyte. If the electrolyte is working and doing its job as a wire carrying the current to the cathodes, what we have here then is a resistance effect that changes the applied current density to the exchange current density. It changes the amplitude of the wave local to and responding to the change in the substrate. What this does, it'll change the rate of growth locally, therefore increasing oxide roughness, therefore increasing the internal stress of the oxide forming. And in worst cases, it can cause actual defects like cracking or even burning. But the growth continues as long as we apply that current. And as long as that current is making oxide grow, in other words, it's not being limited. There's no Isabel effects yet. We are going to see that the oxide grows at the highest rate at its center and more slowly and consistently around its circumference. And this growth will continue until the oxide elements impinge on one another. This forms that hexagonal pattern that we recognize as the pattern of the anodic oxide. But it is also the most thermodynamically least energetic pattern that this can achieve. So we can continue to impress our applied current density or applied voltage, but I'm a constant current person myself, and continue to grow this oxide. The electric field forces then transfer themselves because the polarized center doesn't change, but the element has grown. Those field forces are what create the internal pore that allows for ion exchange after the surface is entirely reconstructed by oxide. So ionic conduction becomes the only way to continue to grow the oxide. And that key point number one, that polarization wave, that tracks with the metal oxide interface. As we consume the aluminum, of course, we're also growing oxide outward. So when we transition above the amplitude of that current density wave, we transition from a reaction that is purely non-equilibrium, making pure anodic alumina, to something that sees the equilibrium effects from the electrolyte. We start to see some dissolution. We start to see redeposition of things that have dissolved into the electrolyte and perhaps haven't escaped the current density wave. The structure of the oxide is different from the structure of the metal. But because of the forces generated during surface reconstruction and as we continue to apply the current density, those compressive forces are maintained and the columns grow upward in the direction of the applied current. This is how we form the organized network. The network structure is maintained by the alignment of charge in the oxide, and the oxide growth continues with ionic conduction through the holes in the network structure, but also along the pore. Here is a summary slide that you can refer to later that gives you the steps succinctly with a modicum of explanation. I'd like to now just go into probably the most basic strategy for tuning your oxide structure, and that's looking at the difference between high versus low current density. At nucleation, if we think of polarization as similar to having the same force effects as the poles of a magnet, we can see that if we have a low level of polarization across the surface, that those charges will distribute themselves in frequent smaller nodes across the surface. In contrast, if we have a higher level of polarization, there will be more forces, stronger force between the individual charges on the surface, and these charges will be larger and spaced further apart. Therefore, with surface reconstruction, we will have under the circumstances at lower current density or lower voltage, we are going to have a smaller, finer structure with characteristics such as a central pore or the column wall that'll be finer than when we have a higher current density or a higher voltage. And this is well illustrated by these two photomicrographs. The image on the left is a type 2 anodic oxide grown on 6061 T6 material, and it was grown at 20 degrees C at 1.2 amps per decimeter squared. The dark parallel lines you see are the column walls, and the white radiolucent lines that you see are the central pore. They're extremely fine. You see circular not holes, but bubble-like areas. These are areas where we had magnesium silicide and precipitates that have dissolved in the electrolyte, and they leave empty space behind. The image on the right, and these are at identical magnifications, you please look at the micron marker for 200 nanometers. Do not regard the magnification you're seeing here. It's the micron marker that dictates the magnification. This is also 6061 T6, but it's grown at 0 degrees C and 2.2 amps per decimeter squared, typical type 3 or hard anodizing conditions. And you see dramatically the difference in the oxide structure. Here is the bottom part of the image there where you see the white wavy lines and the black spidery artifact. That's the aluminum itself, and it's showing us that it's crystalline. But the oxide is that columnar structure above it. When you compare the high current density to the low current density, you can see that there are, first of all, fewer columns. The structure is more robust and thicker and beefier on the high current density sample than it is in the low current density sample. So it is possible to tune the oxide structure in a very, very easy and straightforward way. So let's talk now about the impact of the substrate microstructure and the structure of the AAO. So as I spoke to you earlier, as we consider the exchange current density and wanting to grow the most uniform and continuous anodic oxides, which we see very well on the image on the right-hand side, that the best microstructure for anodizing are fine-grained, equiaxed, and homogeneous. And such structures yield the most uniform and continuous oxides. This is a pretty complex substrate. This is a 7000 series alloy. It contains zinc, it contains copper, it contains magnesium. But this is so well processed. The extrusion it exhibits full recrystallization and uniform grain growth, where the alloying elements have remained by and large in solution, except for a few particles here and there. This is a gorgeous microstructure for a very complex alloy. And this is because the anodic oxide is typically transparent. It provides us a lens to view that surface microstructure. The left schematic is of light entering and escaping the AAO, this transparent lens. If we encounter a particle from the microstructure or a line of particles from the microstructure, be it an etched grain boundary or a string of inclusions, this will be replicated in the surface preparation, and we will see that through the oxide. And this is what I want you to take a look at. When you look at this light optical microscope image on the right, you see the grains are well defined, and you see the ghost and shadow of the oxide above. Believe me, you can see these features through the anodic oxide. And this is well displayed in this slide, where I show you for a 7075 T6 extrusion, beautiful equiaxed homogeneous microstructures, all shown beneath, and the respective aftermarket bike headset components anodized to various thicknesses. I'd like to introduce you to my technician, metallographer, and microscopist, Bob. Bob's worked for me for 34 years. And here is Bob's reflection in a very thin, clear anodized finish. And you can distinctly see his arms, and you can see his legs, and even the graduations on the ruler. But as we go thicker, it's no less beautiful, and we need thickness to absorb and maintain dye. Bob's image is less distinct, and even more less distinct. That's a very bad sentence, but even less distinct at 16 microns. So distinctness of image is very possible with the thin oxide on a homogeneous structure, but as we grow to decorate and improve the appearance, we lose that distinctness of image. So look at this microstructure on the bottom right. This is also 7075 T6 material. In fact, this is also part of the same aftermarket bicycle headset. The complaint was, this is too dark. Why doesn't it match? And here's Bob. Bob's nothing more than a shadow. Well, we developed the microstructure through anodizing, and that clear lens is looking directly at that surface. There is no level of recrystallization. In fact, it's been hampered by the structure of the and constituents of the metal itself and how it was heat treated. We see evidence of dynamic recrystallization in the structure. We see a lot of things that keep this dark. Similarly, here we have an example of a equiX fine-grained microstructure, but the structure is so fine that the grain boundary density alone prevents this from being a bright reflective finish. Instead, it is satin in appearance, but there's nothing stronger than a 7475 T6 extrusion. The desire for this component was that it be strong, but the designer wanted the finish to be bright and shiny. It was impossible based on this microstructure. So the work here was to convince, as much as to grow a beautiful oxide, was to convince the designer that a satin finish is a beautiful thing. To go under the hood, let's look at this complex component that is a diesel fuel pump. This is a alloy 383 die casting, and the rotors are electroless nickel-plated steel. Alloy 383 is a high silicon, low copper alloy. What we're seeing in this microstructure is the results of coarse primary silicon particles that exceed 10 microns in size. When we look down at the surface of the oxide, what we see is these have produced a network of cracks over the entire oxide surface. We also see shadows of dark appearing material. And remember what I told you, equilibrium processes will become something to worry about when we exceed the polarization wave. Well, copper that had gone into the electrolyte redeposited on top of the surface of the oxide in areas where resistance was highest. The image on the right is a metallographic cross-section of this material where you see quite well the size, shape, and distribution of large primary silicon particles, as well as silicon needles and other large particles. How do you get around this? Well, you modify the alloy because you are developing the microstructure when you anodize. And by modifying the 383 alloy to A383, which means a small amount of iron was added, we were able to reduce the size and prevent the formation of the primary silicon phase. And even though, remember this, only aluminum anodizes, silicon doesn't anodize. And even though we see here and there small fine particles of silicon in the oxide, our oxide is nevertheless robust, uniform, and consistent across the entire surface. So when we consider the effects of the exchange current density, we see that, and the first thing is engineering performance is optimized when the AAO is uniformly thick and continuous and without defects. And this is what we're after: corrosion protection, wear resistance, clarity, and uniformity of appearance. but the quality of that oxide is intimately linked with the quality of the base material. So consequently, we can say anodizing is a garbage in, garbage out process. There are things we can do, though, to strategize and make things better. And here I'd like to show you just briefly how to connect the anodizing circuit to the quality of the structure. So I need you to remember all the time that virtual picture of the current density wave flowing according to the polarization of the surface. If ever we block that wave, we're cutting that circuit locally. And this can be done on purpose with a mask or by accident with contamination such as machine oils, grease, or dirt. Even residual oxide from previous processes will do this. When we have a short circuit, we cannot grow oxide. And depending on the shape of that dirt, the tenacity of that dirt, and what that oxidation reaction can do around it, we can push these things up and out, which will drastically change the oxide structure, or we will simply have bare metal. On the other end of the spectrum, if we have a very rough, irregular surface, points such as corners or machine burrs will offer us concentrations of charge where the oxide can't grow. But with activity, those burrs will blunt and oxide will then reestablish itself and grow again. And so what we end up having is an oxide develop with internal defects because of the rough, irregular surface. So when these resistance reactions occur, the circuit is impeded, and we see correspondingly an increase in anode temperature. This leads to the dissolution of the oxide at the oxide electrolyte interface. What does that cause on the final oxide product, final anodized product? A reduced surface hardness. And in some cases, in addition to oxide roughness, the oxide might appear frosty. The wear resistance is reduced. When we dissolve the top surface, we close those pores off. Dye uptake is blocked. Dye penetration is inhibited, and we end up having less dye closer to the surface in the oxide structure itself. The dye that is there is trapped. So our result is that the color appears inconsistent or patchy, and we have reduced UV stability. Lastly, we inhibit that equilibrium reaction critical to long life and corrosion protection. We inhibit sealing. The sealing will be confined to the very tippy top of the structure and not penetrate to the 100 nanometers that we expect. The dye that is confined at the surface will be extracted during sealing and further inhibit sealing. And that chemistry will be trapped at the surface and not easily rinsed away. Consequently, in addition to being not attractive aesthetically, our corrosion resistance is reduced. We will see reduced performance during UV exposure, even yellowing, as any organic material is affected by UV exposure. So with that, I think I've achieved our class goals today. And I think that and hope that by connecting the circuit to the mechanism of growth, you can start imagining process strategies that optimize and target the characteristics you desire for your applications, that for your process of anodizing, it is indeed an engineering process. The engineering strategies that can help overcome barriers to oxide growth include recognition of these metallurgical factors, what to do to alter, improve, or make the best of the surface with pre-treatment, to be able to grow the best oxide on the most complex and difficult alloys through various techniques, and to model the circuit so that you can understand for design and function and target troubleshooting. So these are the details that we cover in our School for Anodizers with the AAC. We intend and hope that we can make anodizing for you all an engineering process. Here are some references, including my book, The Metallurgy of Anodizing Aluminum, that was published by Springer Nature. We're a very smart community, but we're not smart alone. Please take a look at these references and if you have questions. And I thank you for your kind attention and would like to ask Scott if we can begin our Q&A.
Thanks so much, Dr. Runge, and also to the Aluminum Anodizers Council for this presentation. We have a lot of questions, so we'll get through as many as we can, but let's go ahead and dive in. So first, what is the anodizing strategy for multi-material body mix in the auto industry?
Can you repeat the question, please? I didn't understand.
What is the anodizing strategy for multi-material body mix in auto industry?
Well, multi-material, are you talking multiple aluminum alloys, or are you talking about aluminum clad steel, or something, something where, you're talking plastics, or and I would need a little bit of clarification to answer that, because there are definite strategies here that sometimes are solved by masking. For example, if this is aluminum clad steel, you have to somehow mask the steel in order to expose the aluminum anode to the electrolyte. Otherwise, you're going to have competing reactions because of the drastically different oxidation potentials between iron and aluminum. So that's that one quick response there. With plastics, you can typically anodize aluminum that may have been co-molded with plastic, but it takes some experimentation and understanding so that you know that you are really making contact to the aluminum and have the best applied current to that component. And this is such a complex question, Scott. Maybe that would be something to take offline in a more detailed email answer.
I think that sounds right. Let's move on to another. What's the best material to use for a cathode? Do they age or get worn out? If so, what do they look like when they are worn out?
Well, honestly, my favorite cathode material is aluminum itself. I know a lot of high throughput industries prefer not to use aluminum because it does dissolve in the electrolyte. And so that addresses that part of the question about how does it wear out? Well, it dissolves. The thing is you can pull the cathodes. They will passivate in the sulfuric acid or whatever acid electrolyte you're using. So the dissolution is limited. But the reason I love aluminum cathodes is because it increases the efficiency of the circuit. It really draws that current to it. You don't want resistance to build up in the electrolyte, because when you have resistance anywhere, you're going to build up a corresponding thermal effect. That thermal effect is detrimental to your oxide, because your oxide, don't forget, we're transitioning from non-equilibrium to equilibrium effects the higher we exceed that current density wave. So when we have our oxide exposed to a hot electrolyte, holy cow, we get dissolution. And this is why the industry in high energy processes such as type 3 anodizing, they will chill the electrolyte. But I've often seen that chilling the electrolyte is very bright to do in high throughput processing, such as architectural anodizing, especially during summer months when everything is hot. So if we are not using efficient cathodes, that these results will happen sooner. So there are a lot of people that, years ago, our cathodes used to be lead. And we didn't care so much because we weren't so savvy about what was going on in the process. We're a lot smarter today. And lead is heavy. It's not very conductive at all. You would get a lot of heating and you would spend a lot of money chilling. On the other side, stainless steel, albeit rather robust, you're dissolving iron then into your electrolyte, and the effects of those colors, of those elements, can impart color to the oxide, which is undesirable. Don't forget what I showed you on the fuel pump, those dark shadowy areas, which was redeposited copper. You don't want anything like that happening because it does change the appearance of the oxide. Another type of cathode is graphite. And graphite is nicely inert and stable, but graphite has about the conductivity of it's not as conductive as aluminum, and where it doesn't degrade as much. If you're running complex alloys, you can run into problems with that circuit efficiency pulling that current away. So I'm talking anodizing strategies here. And you have to strategize according to the demands of your process. I love an efficient process, but as I'm driving several linear feet of sheet material through my baths, am I heating the bath up enough that I'm dissolving too much aluminum into the bath, which changes the resistance of my electrolyte wire? I might prefer to slow things down a little bit and run with graphite. So these are the strategies that we can discuss in detail in a networking situation or by way of email.
Right. We'll take one more since we're kind of getting close to the hour here. Can you talk about precipitates from aluminum alloys and the effect on AAO structure imperfections and potential crazing and cracking in thermal part cycling?
Okay, well, let's go back. So this is probably the best example I have, and we have a class in Anodizing Essentials that talk about metallurgy basics for anodizing aluminum. That will be offered in November at Surfin, and then again next May at the ET conference. The basic thing to remember is that only aluminum anodizes. Alloying elements precipitates intermetallic particles such as primary constituent phase that forms in the very, castings. Anything that contains aluminum will try to anodize. The presence of alloying elements, like I mentioned with discussing exchange current density, will pose resistance and slow that reaction down. So when we have something here, for example, a large primary silicon particle that is in the surface, on the image on the left, we're looking down on the oxide. We see the bright appearing silicon particles interrupting the continuity of the oxide itself. This is well diagrammed in that dotted blue square on in the left-hand image. These set up stress risers in the oxide itself and cause cracking. When we look at the counterpart to this image, which is the cross-section that is metallographically prepared, we see this basically the same network, but we don't see only large particles causing this. We see small needle particles that are also developing crack equivalents from the interface with the base metal through the oxide to its outer surface. So when we have aluminum there, it will misorient the structure because remember, the oxide is going to grow in the direction of the applied current. If we have a spherical particle, that growth direction will be fanned out according to the radius of that particle. So we will see branching occur in the oxide, and that's very well displayed in this particular image, where we see that we have a particle up here and the oxide grew around it, bifurcating the structure and growing up around it. We see the effect of pockets of empty space due to deformation in the alloy. And we see here the adjacent bases of oxide columns that have let go while the applied current is pushing the electrons through, and we have this incidental pocket of no aluminum. So the structure lets go intermittently till it grows around it, and then order is restored. So this is, I think, Scott, I think I've used up the time. Particles themselves also dissolve in the electrolyte. Magnesium silicides are pretty famous for dissolving in sulfuric acid, and what they tend to leave behind are holes.
Okay. Yeah, I think unfortunately we are out of time. We have a ton of great questions, so I think there's a lot of offline conversations that could happen here. Dr. Runge, thank you so much for your time today. This has been great. I'd also like to say thank you to all of our attendees for taking time to join us today, and thank you to the Aluminum Anodizers Council. We really appreciate everyone being here and hope you'll join us for the next products finishing webinar. For more information, please visit pfonline.com/webinars, and everyone have a great day. Thanks so much.
Thank you, everyone, for your kind attention.